So this experiment is been connected to drop on Filmwise condensation apparatus. So this experiment we have been using to study the heat transfer coefficient and overall heat transfer coefficient for dropwise and filmwise condensation using condensation apparatus. So let us know how this process theoretically works. Condensation is a process of change of phase from vapor to liquid when vapor temperature is reduced below its saturation temperature. This can be done by bringing the vapor into contact with the solid surface whose temperature is below the saturation temperature of the vapor. And condensation may be taken place either by dropwise or a filmwise. If condensation is in the form of small drops, is called as a dropwise, and it is in the form of liquid thin layer or in the form of film is called filmwise condensation. In the film-wise condensation, the surface is covered by liquid film of increasing thickness, and this film acts as a resistance to heat transfer from the vapor to solid. Therefore, heat transfer rate is less in the film-wise condensation. However, in a drop-wise, the vapor is condensed in the form of drops which slides down due to gravity and exposing the surface to the vapor. Hence, in the dropwise condensation case, there is no resistance like a film formation to transfer the heat from the vapor to solid. Therefore, heat rate is high as compared to film-wise. However, it is very difficult to achieve dropwise condensation in practical application. So now we will see the description how this apparatus is being set. The apparator setup consists of metallic container in which steam generation takes place. Here you can see this a metallic container. So where the steam generation is going to take place, a suitable electric heater is installed in the lower portion of the container which heats the water and facilitates steam generation. So at the bottom we have been having a heating coils which when current is passed to this heating coil, from there the heat is being transferred to the water, from that steam is being generated. To regulate the rate of steam generation, the input voltage to the heater can be altered by means of voltage regulator. So here we have been having a voltage regulator. From that we are able to regulate the flow of current. An opening is provided in the cover for filling the water, so this can be opened easily and we can fill the water as per your requirement. The glass cylinder house two water cooled copper condenser, one for which is chromium plated to promote dropwise condensation. Here you can see in the image, this is chromium plated to promote dropwise condensation, and other it is natural state to give filmwise condensation. So pressure gauge is provided to measure the steam pressure, and separate cooling water connections are provided to condenser. A rotometer is provided to measure the flow rate of water supplied to the condenser. So you can see this rotometer from which you can control the flow of the water. A multi-channel digital temperature indicator is being provided to measure temperature of steam, condenser surface, condenser cooling water inlet and outlet. So from this you can see all the form of temperature indicators. So all those things it is been mentioned here in this specification. So T1 for room temperature, T2 water inlet, T3 surface temperature, and T4 water outlet, and T5 surface temperature, and T6 water outlet. Here T3 and T4 for film wise, and T5 and T6 is in a drop wise purpose. So now let us see how the procedure to conduct this experiment. Fill the steam generator with water to little over half, checking the water level by water level indicators. So here we have been having we need to fill up more than half, and we have been having here the pressure gauge, and water indicator is been there so that we can find out how much water is being filled up, which is selected for test and note down the water flow rate from the rotometer. From the rotometer we are able to identify what is in a flow rate. It is recommended to have flow rate between 1 to 2 liters per minute. So then switch on the water heater to generate the steam. Wait till the steam pressure rises to 0.5 kg per centimeter square. From this here pressure gauge we can identify. So we need to wait till the pressure is reached to 0.5 kg per centimeter square. Allow the steam slowly to flow through the glass chamber. As the steam flows over the selected section it gets condensed and falls to bottom of the glass container and drains out through the drain wall. Maintain the pressure in the steam generator constant by increasing or decreasing the voltage across the heater according to various pressure. Depending type of the condenser selected, dropwise and filmwise condensation can be visualized. So note down the water flow rate and steam pressure and the temperature from T1 to T2 in the tabular column. So here we will see the tabular column. So in this tabular column we are going to find out we are going to note down the flow rate of the water, so from the rotometer, and then we have been converting that one into meter cube per second. Then we have been having a stream pressure in bars, it has been there in kg per centimeter square, that is been converted into bar. Then with the help of the temperature indicator we are going to find out the T1 temperature, that is a room temperature, and temperature in degrees, T2 at water and T3 at surface and T4 at the water outlet. So then we are going to find out what is an heat transfer coefficient in watts per meter square per Kelvin through inlet and through outlet, and what is a heat transfer coefficient. In the same way we have been finding out for the dropwise condensation. So here also we are going to note down the water flow rate and the steam pressure and the temperature on the surface and temperature at the outlet. Then we are going to calculate the same thing, the inner heat transfer coefficient and the outer heat transfer coefficient and overall heat transfer coefficient. Now let us look forward for the calculation, how we are going to calculate these things. Now let us see the observation, what are the values you have been having. The copper tube condenses for the filmwise condensation. We have been having the inner diameter, outer diameter and length of the tube. Inner diameter it has been given 22.8 mm and outer diameter that is 25 mm and length of the tube that is 135 mm. So then chromium plated condenser for dropwise condensation. The inner diameter is 22.8 mm and the outer diameter 25 mm and the length of the tube that is 135. Here you can see that the dropwise and filmwise material what they have been taken, that is here for the filmwise that is in a copper tube and for dropwise it is in a chromium, but the dimension remains same thing. So here the T1 here what you have noted down the temperature, that is in a water inlet temperature in Kelvin, and T2 is in a water outlet temperature of the copper condenser, that is also in degree Kelvin, and T3 is water outlet temperature of the plate condenser. T4 is a surface temperature of copper condenser in degree Kelvin, and T5 the surface temperature plated condenser in degree Kelvin, and T6 the glass chamber temperature. So now we will see the calculation. Here overall heat transfer coefficient based on inner surface area is given by U0, that is equal to 1 by